Just look at that bridge. It's been standing for centuries, stone by stone, arch by arch, defying time, weather, even the relentless flow of the river itself. How did medieval builders, with no steel, no machinery, not even the basic math we take for granted today, create structures so enduring they still capture our imagination? There's something almost magical about these ancient crossings. They weren't just practical pathways, they were lifelines connecting towns, enabling trade, and embodying the sheer ambition of the human spirit in an age of profound limitation. Every time you walk across one, you're stepping into a story, one written in stone, mortar, and mystery. Today, we're going to journey back into that world. We'll uncover the hidden techniques, the quiet innovations, and the ingenious problem solving that allowed medieval engineers to achieve what many would have called impossible. This isn't just a story of architecture, it's a testament to human creativity, perseverance, and the timeless desire to reach beyond what seems attainable. These builders didn't have textbooks or engineering degrees. What they did have was observation, experimentation, and a deep understanding of materials and forces that often feels lost to time. So if you've ever wondered how these magnificent bridges were made, how they supported immense weight, withstood floods, and became centers of community and commerce, you're in the right place. We're going to explore the secrets behind their construction, from the foundational myths to the very real, very brilliant methods that turned dream into stone. This is more than history, it's a window into how people built legends, and how those legends still stand with us today. This explosion of bridge construction wasn't accidental, it was the direct result of a continent in motion. After the relative isolation of the early Middle Ages, Europe was waking up. Trade routes were expanding, carrying not just goods but ideas, and a newfound religious fervor was sending thousands on pilgrimages to sacred sites. Kings and lords, meanwhile, were consolidating power, and that required moving armies and collecting taxes efficiently. A river, once a natural barrier, was now an obstacle to progress and profit. The old fords and ferry crossings simply couldn't handle this new volume of traffic. They were slow, dangerous in bad weather, and often controlled by local nobles who charged exorbitant tolls. A sturdy, permanent bridge solved all these problems at once. Think of the bustling merchant hauling wool from England to the markets of Flanders, or the pilgrim walking from Paris to Santiago de Compostela. For them, a reliable bridge meant safety, predictability, and time saved. It meant not losing a wagon to a swollen river or a life to a treacherous current. This demand created a new class of wealthy patrons, guilds of merchants, prosperous towns, and even the church itself, all willing to invest vast sums in infrastructure that would secure their economic and spiritual interests. The famous London Bridge, begun in the 12th century, is a perfect example. It wasn't funded by the king alone, but by a combination of royal funds and taxes on wool, the lifeblood of English trade at the time. But commerce and faith were only part of the story. The political landscape of the era was a complex puzzle of rival kingdoms and fiefdoms. For a ruler, controlling a key river crossing was a strategic military advantage of immense importance. It allowed for the rapid deployment of troops to defend territory or project power into a rival's lands. The magnificent Pont Vale in Cahors, France, constructed in the 14th century, wasn't just a beautiful feat of engineering with its 3 towering fortified gates. It was a stark statement of military strength and control over the surrounding region. These bridges became choke points and strongholds, their very design incorporating defensive towers, gatehouses, and even drawbridges. So, when we admire these structures today, we're not just looking at transport links. We are seeing the physical manifestation of a changing world, the arteries of a revitalized economy, the pathways of faith, and the strategic chess pieces of medieval power, all carved in stone. Now, with this urgent need for reliable crossings established, we arrive at the first and perhaps most daunting challenge these builders faced. How do you even begin to build a massive stone bridge in the middle of a powerful, flowing river? You can't just start piling stones on the riverbed. The current would sweep them away before the mortar even had a chance to set. The secret, the absolute cornerstone of their entire endeavor, lay in a brilliant and often overlooked technique for creating a temporary dry workspace right on the river floor. They mastered the art of building a cofferdam. This wasn't the massive steel-walled structure we might think of today. Their cofferdam was a testament to working in harmony with nature, using the materials they had in abundance, timber and clay. The process began by driving two tight, parallel rows of long, sharpened wooden piles deep into the riverbed, creating a rectangular enclosure around the area where a bridge pier was destined to stand. The space between these two walls of timber was then meticulously packed full of thick, wet clay. This clay was the magic ingredient. When compressed, it became almost completely watertight, creating a formidable barrier that held back the river's force. Imagine the scene: a team of workers, likely using a large, manually operated pile driver. A heavy weight lifted and dropped rhythmically by ropes hammering those logs into place against the relentless push of the water. Once the clay seal was complete, the real work could begin. Using buckets and simple pumps, often Archimedes screws turned by manpower or even a water wheel, they would tirelessly bail the water out from inside this enclosed box. Slowly and miraculously, the riverbed within the cofferdam would be revealed, a patch of dry ground summoned into existence amidst the flowing current. Here, in this muddy, temporary cell, builders could finally get to work on the permanent foundation. They would excavate down until they reached a firm, stable layer of subsoil, something solid enough to bear the immense weight of the stone pier to come. This foundation itself was often built up from layers of stone and mortar, creating a wide, stable base. The entire process was incredibly dangerous and difficult. The clay seal could spring a leak, the river could rise unexpectedly, and the wooden walls themselves were under constant pressure. But when executed correctly, it provided the one thing essential for a bridge meant to last centuries: a stable, unmoving point to build upon. This clever manipulation of the environment, this ability to briefly tame a river, was the unsung hero that made every magnificent medieval arch above the waterline possible. They may have lacked modern textbooks, but medieval engineers had access to the most impressive engineering library imaginable, the crumbling, yet still standing, remnants of the Roman Empire itself. As they traveled across Europe, these master builders would have encountered Roman bridges, aqueducts, and viaducts, marvels of stone that had already weathered half a millennium. They were reverse engineering genius, studying these ancient structures not to simply copy them, but to understand the core principles and then improve upon them for their own age. The most critical lesson they took was the power of the arch. The Romans perfected the semicircular arch, a magnificent and powerful shape that efficiently distributes weight down through the piers and into the ground. But medieval builders observed a key weakness in this design, especially for bridging wide rivers. A perfect semicircle is very tall. To cross a broad waterway with a series of these arches, you would need incredibly high, elevated roadways or very tall piers built deep in the dangerous river current. The medieval solution was a stroke of geometric brilliance: the pointed Gothic arch. This wasn't just an aesthetic choice to match their cathedrals, it was a profound engineering innovation. By using a pointed arch, builders could achieve a greater span between piers without increasing the height of the arch itself. This meant they could use fewer piers to cross the same width of river. Fewer piers in the water was a massive advantage. It reduced the obstruction to flow, making the bridge far more stable during floods, as water and debris could pass through more easily. The pointed arch also directed forces more vertically down into the piers, allowing for taller, slimmer, and more elegant structures that still possessed immense strength. The Old Bridge in Regensburg, Germany, is a stunning example of this evolution, its distinct pointed arches allowing it to defy the powerful Danube River for over 800 years. They also innovated in the pier design itself. Many medieval bridges feature another clever addition: starling cutwaters. These are the triangular or rounded extensions built onto the upstream side of the piers. Far from being mere decoration, these starlings are like the keel of a ship, expertly designed to cut through the flow of the current, diverting water smoothly around the pier and reducing erosive pressure on the foundation. They also serve to break apart logs or other debris that might crash into the bridge during a flood, acting as a defensive shield for the vital structural components. So while the Romans provided the foundational blueprint, medieval builders refined it, transforming the robust Roman arch into a more adaptable, efficient, and resilient form that was perfectly suited to the challenges and ambitions of their own time. This geometric shift was far more than a stylistic flourish to match the grand cathedrals of the era. It was a fundamental rethinking of structural physics that solved one of the semicircular arch's greatest limitations. A perfect Roman arch is, by its very nature, incredibly tall relative to its width. To span a wide river, you would either need a single, impossibly large arch or a series of many smaller ones, which meant constructing numerous piers right in the deepest and most treacherous parts of the current. The pointed arch elegantly sidestepped this entire problem. By rising to a point, builders could achieve a wider span between supports without increasing the overall height of the arch itself. This immediately meant fewer piers were needed to cross the same stretch of water, which was a monumental advantage. Fewer obstructions in the riverbed allowed water to flow more freely, drastically reducing the scouring effect of currents and the dangerous buildup of flood debris against the bridge's foundations. The real genius, however, lies in how the pointed arch manages force. A semicircular arch pushes outward against its supports with a significant lateral thrust. The wider the span, the stronger this sideways push becomes, requiring massive, bulky piers and sturdy abutments to contain it and prevent the entire structure from collapsing. The pointed arch, by contrast, channels a greater proportion of its load more directly downward into the vertical piers. This more efficient distribution of weight meant the piers themselves could be built taller and relatively more slender without sacrificing an ounce of strength, giving these medieval bridges their characteristically graceful, soaring appearance. The structure became less about brute force and more about intelligent force management. We can see this revolutionary principle brought to life in bridges like the Pont de Saint-Bénézet, the famed Avignon Bridge in France. While its Romanesque beginnings used round arches, later reconstructions and many of its surviving spans showcase the pointed Gothic style. This design allowed it to stretch farther across the powerful Rhone River with a confidence a purely semicircular structure could never have mustered. The pointed arch provided the medieval engineer with a new kind of flexibility, allowing them to tailor the steepness of the arch to the specific needs of the site. A flatter arch for a wider span, a steeper one for a more forceful downward thrust. It was this adaptability, born from a deep observational understanding of geometry and load, that turned ambitious architectural dreams into enduring stone reality. But achieving this grand architectural vision required more than just clever design. It demanded an almost supernatural level of craftsmanship at the most fundamental level, the stone itself. We've marveled at the arches, but we must look closer at the individual blocks that form them. How did these masons, working with rudimentary tools, achieve such flawless fits that their joints are often tighter than a modern credit card? The secret was a combination of artistry, proprietary knowledge, and tools that were far more sophisticated than we often give them credit for. The process began at the quarry, where selecting the right stone was paramount. Master masons would seek out dense, durable rock like sandstone or limestone, and they would listen to the quarry face by tapping it with a hammer. A clear, ringing sound indicated solid, flawless stone, while a dull thud might reveal hidden cracks or faults that could spell disaster centuries later. Once selected, the rough blocks were shaped by apprentices using a tool called a pitcher, a heavy, pointed chisel struck with a mallet to split the stone along its natural grain. But the real magic happened during the finishing process. For this, the key instrument was the chisel, but not just one type. A mason's toolkit contained a variety of them: point chisels for roughing out shapes, claw chisels for fine detailing, and perhaps most importantly, the flat chisel for creating those impeccably smooth surfaces. The final finish was often achieved by laboriously rubbing the stone with a flat piece of an even harder rock, like granite, along with sand and water as an abrasive. This painstaking process could take days for a single block, but it resulted in faces so perfectly true that when placed together, they transferred load with breathtaking efficiency. Yet, even the most perfectly cut stone is useless without the glue that holds it all together, the mortar. This was perhaps the most closely guarded secret of the medieval masons' guilds. Their recipes were not the simple sand and lime mixes we might assume. They were complex, almost alchemical formulas, often unique to a specific lodge or even a single master. The base was quicklime, produced by burning limestone in incredibly hot kilns. This was then slaked with water to create a putty that was left to mature, sometimes for years, in sealed pits. This aging process allowed it to develop a creamy, plastic quality, but the true innovation was in the additives. Archaeological analysis of ancient mortar has revealed fascinating inclusions. Some builders mixed in crushed brick, tile, or even volcanic ash, known as pozzolana, a technique they learned from studying Roman ruins. These ingredients contain silica and alumina, which react with the lime in a process called pozzolanic reaction, creating a mortar that is not only strong but actually waterproof and capable of curing underwater, a vital trait for bridge piers. Other recipes included animal blood, hair, or eggs. While the exact chemical benefit of these organic additives is still debated, it's believed they might have altered the mortar's working properties, reducing cracks as it cured and creating a tougher final product. This mortar wasn't just glue. It was an engineered material designed to work in partnership with the stone, flexing slightly under pressure and distributing stress, which is a key reason these structures could withstand centuries of vibration and movement without shattering. The stone provided the strength, but this secret, sophisticated mortar provided the resilience. And it's this very mortar that holds one of the most fascinating and enduring secrets of medieval bridge building. We look at these structures and see stone, but the true longevity, the hidden resilience, often came from the mix in between. While we might think of historical mortar as a simple, weak glue, the reality is that medieval masons developed complex, proprietary recipes that functioned more like a modern engineered compound, gaining strength over centuries in a way that sometimes surpasses the capabilities of our own Portland cement. Theirs was a chemistry of practicality and observation, a form of material science passed down through guilds and often kept as closely guarded secrets. The base of most medieval mortar was lime, created by roasting limestone in a kiln to produce quicklime, a volatile and dangerous substance. This was then carefully slaked with water, a process that releases tremendous heat and results in a lime putty. But here's where the masters diverged from the basics. This putty wasn't used immediately. It was often left to mature in a pit, sometimes for months or even years. This aging allowed for a more complete chemical reaction, resulting in a finer, more plastic, and ultimately stronger binder. Yet, the pure lime mixture, while good, wasn't enough for the brutal, wet environment of a bridge pier. This is where the mysterious additives came in, each serving a specific purpose discovered through tireless experimentation. Some builders, particularly those with access to volcanic regions or Roman ruins, incorporated pozzolana, a fine, siliceous volcanic ash. The Romans had mastered this, and medieval engineers were quick to recognize its value. When mixed with lime and water, pozzolana triggers a pozzolanic reaction, creating calcium silicate hydrate. This is the same compound that gives modern concrete its strength, and it has a miraculous property. It can cure and harden underwater, making it absolutely perfect for the submerged portions of a bridge. It creates a mortar that is not just strong, but genuinely hydraulic. But not everyone had a volcano nearby, so they innovated with what they did have. Crushed brick, tile, and even certain types of clay were discovered to have similar, if slightly less potent, pozzolanic properties. By adding these crushed ceramics, they were effectively creating an artificial pozzolana, a brilliant workaround that delivered similar waterproofing and strengthening benefits. Then we have the more enigmatic ingredients, the ones that sound like they're straight out of an alchemist's handbook. Animal blood, egg whites, cheese, and even beer. While their exact contributions are still studied, the leading theory is that these organic materials acted as air entraining agents. When mixed into the mortar, proteins from blood or eggs could create millions of microscopic air bubbles. This might sound counterintuitive for strength, but it's actually genius. These tiny bubbles provide minuscule chambers for water to expand into when it freezes. Without them, water trapped in the mortar would freeze, expand, and create tiny cracks that would worsen over winters, slowly spalling the stone and crumbling the joint. The organic additives gave the mortar a flexibility and freeze-thaw resistance that pure lime mortar lacks. They essentially invented their own antifreeze, a resilience that allowed the bridges to withstand hundreds of harsh winters without failing. So the next time you see a medieval bridge standing strong, remember that its endurance might be due to a forgotten recipe of lime, ash, and perhaps, just perhaps, a little bit of ancient magic mixed with everyday ingenuity. But these stone canvases were not solely for divine protection. They also served a far more earthly and secretive purpose. Walk across the parapet of a medieval bridge, and you might notice something else: seemingly random marks scratched into the stone. A series of circles, a unique letter, a distinctive symbol that looks like a brand. These are the mason's marks, the hidden signature of the craftsman who shaped that very block. In an age before formal contracts and printed business cards, these marks were a sophisticated system of accountability and quality control. Each mason had his own unique symbol, registered with the guild. When the quarterly wages were paid, the master builder could walk along the construction and see exactly who had carved which stone. A poorly cut block could be traced directly back to the man responsible, ensuring that only the highest standard of work was accepted. But these marks were more than just signatures. They were a form of silent language among the initiated, a way to identify a fellow guild member's work and perhaps even denote his level of skill or the specific lodge he hailed from. This duality of meaning, the public symbol for spiritual defense and the private mark for professional pride, extends to the very figures that adorn these structures. Take the famous bridge devil, found on structures like the Pont Tray. This mischievous gargoyle isn't merely a decorative grotesque, it's a character from a popular legend. The story goes that the master builder, struggling to complete the bridge on time, made a pact with the devil. Satan would help with the construction in exchange for the soul of the first to cross. Upon completion, the clever builder outwitted the devil by sending a dog across first. In fury, Satan supposedly returned each night to dislodge the final stone in the central tower, forcing workers to constantly reset it. The carved devil is a permanent reminder of this tale, a warning against temptation and a celebration of human cunning triumphing over evil. It's a piece of folklore literally set in stone, making the bridge not just a feat of engineering, but a storybook you can walk across. Other common symbols carried deeply layered meanings. The Sheila Nagig, a startling figurative carving of a woman displaying her exaggerated genitals, appears on some older bridges, particularly in Ireland and Britain. To the modern eye, it seems shocking and out of place, but scholars believe it was an ancient apotropaic symbol meant to ward off evil and death by invoking the powerful, life-giving forces of birth and fertility. Its confrontational imagery was designed to frighten away malicious spirits, much like the grotesque gargoyles on cathedrals. A simple cross might signify a prayer for safe passage, while a pentagram, often misunderstood today, was frequently used in medieval times as a symbol of the 5 wounds of Christ and was another powerful protector against evil. Every niche, every worn sculpture, every strange sigil was a deliberate choice, a layer of meaning embedded into the infrastructure. These bridges were built to last not only physically but spiritually and culturally, their stones whispering secrets of faith, folklore, and the fraternity of the hands that shaped them. Yet for all their spiritual and defensive significance, these bridge-top settlements also represented one of the most ingenious and pragmatic economic models of the medieval world. Building a bridge was astronomically expensive, requiring not just skilled labor but vast quantities of stone, timber, and iron, maintaining it against the relentless assault of floods, ice, and where was a perpetual financial burden. So how did a town or a religious order fund such a monumental, ongoing project? The answer was to make the bridge itself a source of revenue, a literal street of commerce. By constructing shops and houses directly on the structure, the bridge's custodians created a continuous stream of rental income dedicated solely to its upkeep. The famous London Bridge became a veritable thoroughfare of life, with its famous multi-storied buildings jutting out over the Thames, housing everything from prosperous merchants to humble shopkeepers. The rent from these properties paid for the bridge master and his team of maintenance workers in perpetuity, ensuring that the structure that generated the wealth was also preserved by it. This fusion of the sacred and the commercial created a unique microcosm of medieval society, a bustling, vibrant community suspended between two riverbanks. A pilgrim crossing the bridge could venerate a saint's relic in the chapel, purchase a badge to prove they'd done so from a vendor right outside, then rent a room for the night in a bridge-top inn, all while being protected by the garrison in the Tower Gatehouse. The bridge was not merely a crossing, it was a destination in itself, a secure and privileged space where trade was guaranteed protection, and travelers were a captive market. This self-sustaining ecosystem ensured the bridge's survival long after its original builders were gone, turning a piece of critical infrastructure into a living, breathing, and profit-making entity. The stones themselves tell this story of layered purpose where faith offered safe passage for the soul, commerce funded safe passage for the body, and together, they created something far greater than the sum of their parts. Yet this thriving community on the bridge was also incredibly vulnerable, a fact medieval planners understood all too well. A bridge was a vital economic lifeline, but in times of conflict, it became the most tempting of targets, a choke point that could strangle a city's supplies or provide an invading army with a direct route into its heart. To solve this problem, builders integrated a second, more formidable layer of design, transforming these peaceful crossings into some of the most sophisticated fortifications of the age. The bridge wasn't just built, it was armed. The first and most iconic line of defense was the drawbridge. We often picture a simple wooden platform on chains, but its engineering was remarkably clever. Located at one or both ends of the bridge, the drawbridge was a counterweighted beast. Massive timber beams, often shod with iron, were pivoted on huge axles set deep into the stonework of the gatehouse. Their inner ends were attached to enormous counterweights, usually boxes filled with tons of stone or lead, hidden within the gatehouse structure. In times of peace, the weights were lowered, holding the bridge deck level for traffic. But at the first sign of threat, guards would release a locking mechanism. The heavy counterweights would drop, violently lifting the entire timber span into a vertical position in a matter of seconds, sealing the bridge off completely and presenting a sheer, impassable wall to any attacker. This wasn't just a barrier, it was a psychological weapon, a dramatic and unmistakable declaration that the passage was closed. But breaching the drawbridge was only the first nightmare an attacking force would face. Next, they would find themselves trapped in the killing zone, the gatehouse itself. These were not simple arches but multi-storied stone fortresses built directly onto the bridge, complete with battlements, arrow slits, and portcullises, heavy iron or timber grills that could be dropped vertically from slits in the ceiling to further compartmentalize and trap enemies. The true horror, however, awaited them from above. The ceilings of these gatehouse passages were often pierced with carefully designed openings known as murder holes. These were not for dropping coins or messages. They were specifically engineered for defensive brutality. From rooms above, defenders could rain down a relentless torrent of death onto anyone trapped below, not just the legendary boiling oil, which was expensive and rare, but more commonly quicklime to blind and choke, burning sand that could seep through armor, rocks, or simply cauldrons of scalding water. The gatehouse turned the essential act of crossing into a deadly funnel, where an army's greatest asset, its numbers, became its greatest liability. This architectural ingenuity extended to every element of the bridge's martial design. The parapets themselves were often designed as crenellated battlements, providing cover for archers and crossbowmen. The bridge's piers were sometimes connected by secret underwater passages or had lower-level sally ports, allowing defenders to launch surprise attacks on enemies attempting to undermine the foundations from boats. Every stone was placed with a dual purpose, to bear weight and to repel an assault. A bridge like Mono Bridge in Wales, with its formidable, fully integrated three-story gatehouse tower, stands as a perfect testament to this philosophy. It wasn't a bridge with a fort added on. It was a single, unified weapon of stone, a masterpiece of military engineering that declared its purpose to all who approached. Its very existence was a deterrent, a promise of overwhelming defensive advantage that made conquest not just difficult, but catastrophically costly. These incredible feats of engineering and defense came with an equally staggering price tag. We are talking about projects that could take decades, even a century, to complete, consuming the labor of thousands and the resources of entire regions. So, how did medieval society, without modern banks or state budgets, finance these monumental undertakings? The answer is a fascinating patchwork of piety, pragmatism, and pure economic genius that transformed every citizen into a potential investor. One of the most powerful and widespread methods was the formation of a bridge guild or fraternity. These weren't trade guilds in the traditional sense. They were more like charitable organizations with a very specific, holy mission. A bridge guild would be founded under the patronage of a saint, often Saint Benedict, who was considered a protector against the dangers of water. Membership was open to all nobles, merchants, craftsmen, and common folk, and it offered a powerful spiritual incentive. By donating money, materials, or even a day's labor to the bridge, a person was performing a good work, an act of charity that could shorten their time in purgatory. The guilds would organize fundraising fairs, feast days, and even door-to-door collections, creating a steady stream of communal funding fueled by faith. The guild would then manage these funds, often with meticulous records, to pay the master craftsmen and purchase supplies, ensuring the project continued year after year. For larger, more consistent income, there was the toll. The right to collect tolls was usually granted by a king or a local lord, and it was the economic engine that made a bridge sustainable for centuries. But these weren't simple fees. The toll schedules were complex and reflected the vibrant economy of the age. A peasant walking across with a basket of eggs might pay nothing, while a merchant with a wagon full of wool would pay a significant sum. The number of wheels on a cart, the type of goods being transported, even whether animals were being driven to market, all of it had a specified rate. Some bridges even had a unique law called pontage, which allowed the bridge wardens to collect a special toll for a limited period to fund a major repair, essentially a medieval version of an infrastructure bond approved by the crown. Perhaps the most intriguing financial instrument, however, was the sale of indulgences by the church. The theology behind this was profound. Contributing to a holy work, like building a bridge that aided pilgrims on their way to a shrine, was a meritorious act. The church could grant an indulgence, a partial remission of the temporal punishment for sins, to those who donated. This wasn't a get-out-of-hell-free card as it's sometimes mischaracterized, but for a believer, it was a powerful incentive. Preachers would travel from town to town, delivering passionate sermons about the bridge's holy purpose and the spiritual benefits of giving. Donors' names were sometimes even recorded in a book of life kept at the bridge chapel, ensuring their charitable act was remembered in perpetuity through prayers. This system effectively monetized faith, turning the deeply held beliefs of an entire population into the capital needed to lay the next course of stone. It was a partnership between the earthly and the divine, where a coin given for a bridge was an investment not just in safe passage, but in the salvation of one's own soul. These brilliantly fortified and expensively funded structures still faced one of nature's most relentless and destructive forces, the crushing power of winter ice. In colder climates, a freezing river presented a unique and terrifying challenge. As temperatures dropped, sheets of ice would form on the surface, but when a thaw came or the water level rose, these sheets would break apart into massive, sharp-edged flows. Driven by the powerful current, these floating islands of ice became battering rams, capable of slamming into a bridge's piers with enough force to crack stone and undermine the very foundations that had taken years to build. To survive, a medieval bridge couldn't just be strong. It had to be smart, designed to outmaneuver the ice rather than simply withstand its blow. The most common and effective solution was an innovation we touched on earlier, the starling. But its role in combating ice is so critical, it deserves a deeper look. While we often admire the elegant arches above, it's the rugged, often underwater shapes of the starlings that truly tell the story of this battle. These were not delicate additions. They were massive, angular or semi-circular projections of masonry built onto the upstream side of the piers. Their primary function was hydrodynamic. By presenting a sloped, angled face to the current, the starling didn't just resist the flow of water and ice, it actively redirected it. Think of it like the prow of a ship cutting through waves. An incoming ice flow would be guided up and over the sloping surface of the starling. Its destructive energy spent sliding harmlessly over the top of the pier instead of delivering a direct, shattering impact to its vertical face. This simple yet profound geometric trick transformed a blunt force impact into a glancing blow, dispersing the energy of the collision across the entire robust mass of the foundation. For the most extreme environments, engineers developed an even more aggressive design, the icebreaker pier. This was a specialized pier, often broader and more robust than the others, positioned at a strategic angle to the prevailing current. Unlike a standard pier that stands perpendicular to the flow, an icebreaker pier was set at an acute angle, its sharp, reinforced edge facing directly upstream. This design wasn't about deflection, it was about division. Its sole purpose was to actively split large ice sheets as they approached. A massive sheet of ice, sometimes spanning a significant portion of the river, would catch on this forward-pointing edge. The immense pressure of the current behind it would then force the ice to crack along this natural fault line, breaking it into smaller, far less dangerous fragments that could then pass harmlessly through the bridge's arches. The pier essentially used the river's own immense power to break the ice apart, a breathtaking example of medieval engineers working with natural forces rather than against them. This constant, seasonal battle left its mark on the bridges themselves. If you examine the starlings and piers of ancient northern bridges like the Charles Bridge in Prague or many of the bridges over the Rhine, you'll often find them sheathed in rough, durable stone, sometimes noticeably different from the finer ashlar used for the arches above. This was purposeful. This protective cladding was meant to be sacrificial. It was understood that these elements would take the brunt of the abuse from ice, debris, and water. By using a harder, more resilient stone for this armor, and designing it to be relatively easily replaced, the builders ensured that when damage inevitably occurred, it would be to this outer shell, not to the critical structural core of the pier. It was a modular, maintainable defense system engineered for centuries of service. Every spring, as the ice retreated, bridge wardens would inspect this stone armor, ready to repair or replace any sections that had been worn down by the frozen assault, ensuring the bridge's heart remained protected for the winter yet to come. Yet for all the permanence of stone, the true secret to raising these magnificent arches was something utterly temporary. A complex and costly wooden skeleton that would be seen by very few and remembered by even fewer, the centering. Before a single stone of the arch could be set, builders had to first construct its perfect negative, a wooden framework that would hold every voussoir, the wedge-shaped arch stones securely in place until the very last piece, the keystone, was dropped into position. This framework was far more than simple scaffolding. It was a precision-engineered structure that had to be perfectly shaped, incredibly strong, and yet designed to be disassembled and removed once its work was done. Constructing a centering was a major project in its own right, often requiring a separate team of highly skilled carpenters working in close collaboration with the master mason. The process began with the carpenter drawing full-scale plans for the wooden ribs directly onto the floor of a large, flat workspace called a tracing floor, using chalk or charcoal. These ribs, cut from massive, curved oak beams, formed the primary support for the arch's curve. Dozens of these ribs would be spaced closely together across the width of the bridge, creating the full profile of the arch. They were then tied together with horizontal timbers and braced with diagonal supports, creating an immensely strong, rigid lattice that could support the staggering weight of tons of stone and the masons working upon it. The true ingenuity, however, lay in its temporary nature and its potential for reuse. A well-built centering was an enormous investment of time and valuable timber. For a major bridge project with multiple identical arches, it made perfect economic sense to build one centering and then reuse it for each successive arch. This required meticulous planning. Once an arch was complete and the mortar had sufficiently cured, the centering had to be carefully lowered. This was achieved through a clever system of wedges and supports called needles. Workers would gradually loosen these wedges, lowering the entire wooden framework in a controlled, even manner to prevent any uneven stress on the new stonework. The centering would then be disassembled, floated on barges to the next pier, and painstakingly reassembled, its precise shape ensuring every arch in the bridge was an exact duplicate. This practice not only saved tremendous resources, but also guaranteed a uniformity that contributed to the bridge's overall structural integrity and aesthetic harmony. The centering was the phantom limb of medieval engineering, a temporary but essential exoskeleton that gave form to ambition, only to vanish without a trace once its stone counterpart could stand on its own. Considering the sheer scale and complexity of these projects, it's hardly surprising that many medieval bridges took generations to complete. We're not talking about a construction project that pauses for winter. We're talking about endeavors that could span the entire working life of a master mason and that of his son, and even his grandson. The timeline for a bridge like the Charles Bridge in Prague, for instance, stretches across most of the 14th century. This wasn't due to a lack of skill or will, but rather a relentless series of practical, financial, and environmental battles that had to be fought and won season after season. The rhythm of construction was dictated almost entirely by the weather. The all-important work on the foundations, the driving of piles and the building of cofferdams, could only happen during the low water season, typically in the late summer and early autumn. This created a frantic, intense period of activity where crews worked from dawn to dusk, knowing they had a very narrow window to expose the riverbed and lay the critical footing for a single pier before the rains returned and the water rose. Then, as winter set in, work would often grind to a complete halt. The quarries froze, making it impossible to cut new stone. Transporting heavy materials along icy, muddy roads became a logistical nightmare. The site itself, exposed on the river, was treacherous for the workers. This seasonal stop-start pattern alone could add years to a project. Then there was the constant specter of funding. Unlike a modern public works project with a secured bond or government budget, medieval bridge building relied on a precarious and often intermittent stream of income from tolls, indulgences, and donations. A single poor harvest, a local conflict, or the death of a wealthy patron could instantly dry up the funds needed to pay the skilled masons and purchase supplies. Work would stop for months, sometimes years, until enough money could be scraped together again. During these long pauses, the partially built structure was incredibly vulnerable. Incomplete piers could be scoured and undermined by winter floods, undoing years of painstaking work and requiring expensive repairs before new construction could even begin. The unfinished skeleton of the bridge became a familiar, if frustrating, part of the city's skyline for decades. This stop-and-start nature had a fascinating, unintended consequence. It created a living archive of evolving architectural styles and engineering knowledge right there in the stonework. A bridge begun in the late Romanesque period, with its characteristic rounded arches, might finally be completed 200 years later in the high Gothic style, its later arches distinctly pointed. The masons who finished the project were often interpreting the plans and intentions of masters who had died generations before. They had to adapt new techniques to old foundations, creating a unique hybrid structure. The most telling evidence of these long timelines can often be found in the piers themselves. Archaeologists studying the foundations of old bridges sometimes find that the later piers are spaced farther apart than the earlier ones. Why? Because during the decades of construction, the understanding of the pointed arch's superior strength had become more widespread. The newer master builders, confident in the new geometry, could span greater distances with fewer supports, adapting the original design based on a century of accumulated practical experience. The bridge itself became a timeline of technological progress, its stones whispering the story of an engineering revolution that unfolded not in a lab, but over the relentless, patient flow of a river. And behind every stone laid, every arch raised, and every foundation driven deep into the riverbed, stood an army of labor that history has often overlooked. We rightly celebrate the genius of the master mason, but his vision was brought to life by a vast, diverse, and often anonymous workforce. This was not a single team but a constantly shifting tapestry of manpower, drawn from every level of medieval society through a complex web of obligation, necessity, and opportunity. The backbone of this labor force was provided by the system of corvée labor, a feudal obligation that required peasants to provide a certain number of days of free work each year for their lord or for public works projects. For a bridge that would benefit the entire region, easing the travel of their own goods to market, this duty was often enforced with particular vigor. Imagine these men, leaving their fields during the crucial planting or harvest season, traveling to the riverbank to engage in the most back-breaking tasks. They were the ones digging trenches, hauling timber, moving immense quantities of stone and sand from barges, and mixing the vast vats of mortar. Their work was unskilled but utterly essential, the human machinery that prepared the stage for the craftsmen. This was not a choice, it was a tax paid with sweat and muscle, a direct contribution from the common people to an infrastructure that would, in theory, serve them for generations. Yet, skilled hands were needed for the precise work, and these experts were a different class entirely. The master mason, or magister lapicida, was the CEO and head architect rolled into one. He was a highly educated and well-traveled professional, often moving from one grand project to another across Europe, bringing with him a portable library of design knowledge and a team of trusted senior craftsmen. Beneath him were the journeyman masons, the true artists of stone. These men could precisely shape a voussoir block with nothing but a mallet and a chisel, ensuring its faces met at perfect angles to form the seamless curve of an arch. Their expertise was so valued that they were often paid by the piece, so much per finished stone rather than by the day, incentivizing both speed and flawless accuracy. But the masons were just one part of a larger guild ecosystem on the site. The project also required the constant involvement of blacksmiths to forge and sharpen thousands of tools, carpenters to build the intricate centering and cofferdams, and carters with their teams of oxen to manage the Herculean task of logistics. Perhaps most intriguing were the sawyers, a two-man team who would work a large pit saw, one man standing on a log above, another in a pit below, to painstakingly cut the massive timbers needed for construction. Each of these trades operated under their own guild rules and privileges, creating a complex, collaborative, and sometimes competitive microeconomy on the riverbank. Then there is the darker, more shadowy segment of the workforce, forced labor. Historical records from projects like the Charles Bridge and others make passing reference to the use of prisoners and convicts, their sentences commuted to hard labor on the dangerous construction site. This was grueling, high-risk work with little reward, manning the pumps in a leaking cofferdam, handling heavy materials in precarious positions, and working through the harsh winter months. Theirs was a contribution born of punishment, a hidden cost written not in the financial ledgers but in human suffering. The magnificent bridge standing serene today is, in part, a monument to their unseen and uncompensated toil. This multifaceted army, from the obligated peasant to the esteemed master, from the skilled smith to the condemned prisoner, reveals the true social engine behind these wonders. They were not built by a single hand, but by the entire layered structure of medieval society itself, each person leaving an invisible mark on the stone. They may not have used the complex calculus or algebra we learn in schools today, but to say medieval builders lacked mathematical knowledge is to profoundly misunderstand their genius. Theirs was not a mathematics of abstract equations on a chalkboard. It was a living, breathing mathematics of rope, wood, and stone, a practical, applied geometry that was every bit as sophisticated and far more directly suited to the task at hand. This knowledge was the true secret sauce, a closely guarded curriculum passed not through universities, but from master to apprentice on the job site, forming a continuous chain of understanding that stretched back centuries. The master's primary tool was geometry, and his most important instrument was likely a simple length of rope with evenly spaced knots. With this humble cord, he could lay out the entire plan of a bridge directly on the ground of his tracing floor, using pegs to mark key points. This practice, known as setting out, allowed him to translate a complex three-dimensional structure into a full-scale two-dimensional diagram. He could establish perfect right angles using a 3-4-5 triangle, a rope knotted at 12 equal intervals, stretched to form a triangle with sides of 3, 4, and 5 units, which is guaranteed to create a perfect 90-degree angle. He could bisect angles, find centers, and, most importantly, define the sweeping curves of his arches with absolute precision, all without a single written number or complicated calculation. The design of the arches themselves was governed by a system of perfect proportions, often based on simple geometric shapes like the square and the circle. One of the most common methods was the hidden geometry of the pentagon. A master might begin the design of a pointed Gothic arch by inscribing a pentagon within a circle. The intersecting chords of this pentagon naturally create a series of ratios and angles that define the arch's elegant, soaring shape. This wasn't arbitrary. These proportional systems, often linked to what was seen as divine geometry, produced structures that were not only beautiful to look at but also inherently stable because their geometry naturally managed structural forces efficiently. The same harmonic ratios found in the musical scales of the time were literally set in stone in the bridge's design. This practical geometry extended to every aspect of the build. Determining the correct thickness for a pier wasn't a guess. It was a calculation based on the arch's span and the estimated load it would carry, all derived from geometric rules of thumb perfected over generations. A master knew that a pier's width should be roughly 1/4 to 1/3 of the arch's span for a semicircular Roman arch, but could be slightly narrower for a pointed arch thanks to its more efficient force distribution. Even the intricate stone cutting relied on geometry. Each unique voussoir block for a curved arch was a complex trapezoidal wedge. The mason would use a wooden template, called a patron, which was derived from the master's full-scale rope diagram on the tracing floor. He would trace this template onto his rough stone block and then chip away everything that wasn't the perfect shape, ensuring every piece fits seamlessly with its neighbors. This vast repository of knowledge was the exclusive property of the masons' guilds, protected with fierce secrecy. An apprentice would spend years performing menial tasks, simply observing and absorbing the culture of the lodge, before ever being allowed to touch a chisel to fine stone. His real education was in the oral traditions, the cryptic sayings, and the hands-on demonstration of these geometric secrets. Advancement to journeyman and eventually master status required not just skill, but the internalization of this entire system of applied knowledge. It was a holistic understanding that fused math with material science, an intuitive grasp of how stone would behave under pressure, and how geometric forms could be used to harness and redirect the immense forces of weight and water. Their textbooks were the monuments left by their predecessors, and their formulas were the proven proportions that allowed those structures to stand the test of time. But building the bridge was only half the battle. The true test of a community's commitment was the endless, silent war against decay. A A stone bridge might seem eternal, but it is constantly under assault. Water seeps into cracks and freezes, expanding and slowly spalling the stone. Relentless river currents scour the foundations, undermining their stability. The very weight of the traffic it bears causes gradual, imperceptible settling. Without a dedicated, well-funded system of perpetual maintenance, even the grandest bridge would succumb within a few decades. Medieval societies understood this intimately, and they developed remarkably sophisticated and resilient systems to ensure their vital crossings would endure, generation after generation. One of the most fascinating and unique figures in this ongoing effort was the bridge hermit. Far from being a solitary recluse seeking isolation, a bridge hermit was a very public servant, often appointed by the local bishop or town council. His hermitage, a small stone cell built right into the bridge's structure, was his command post. His duty was twofold, spiritual and practical. He was expected to offer prayers for the safety of travelers and to maintain a perpetually burning lamp in the bridge chapel as a guiding light and a spiritual safeguard. But his hands were never idle. His daily rounds involved inspecting the masonry for new cracks, checking the timber decking for rot, and ensuring the drawbridge mechanisms were well greased and functional. He was the bridge's full-time custodian, its first line of defense. In exchange for this vital work, he was granted a small stipend, a place to live, and the right to collect alms from grateful travelers. He was the ever-watchful guardian, a living emblem of the bridge's importance to both the physical and spiritual well-being of the community. For larger repairs that were beyond the hermit's capability, funding was secured through ingenious and permanent financial instruments. The most common was the establishment of a dedicated bridge estate or trust. Wealthy patrons, guilds, or the town itself would donate parcels of land, entire farms, or rental properties. The income generated from these assets, the rent from tenants, the sale of crops or wool was ring-fenced solely for the bridge's upkeep. This created a self-sustaining financial engine that operated in perpetuity, independent of the fluctuating generosity of donors or the municipal budget. The bridge wardens, responsible for managing these estates and commissioning repairs, were some of the most important civic officials. They kept meticulous account books, which still survive today, detailing every expense. So much paid to a mason for resetting 10 stones on the third pier, a sum to a carpenter for replacing planks on the deck, and a payment for a cartload of lime and hair for new mortar. This wasn't charity. It was cold, hard, strategic asset management for the most critical piece of infrastructure in the region. When major disasters did strike, such as a flood washing away several arches, the community would mobilize with remarkable speed. The concept of pontage allowed the bridge authorities to petition the king for the right to collect a special toll for a limited number of years, specifically to fund a large-scale reconstruction. This was effectively a medieval infrastructure bailout, approved at the highest level because the economic and strategic importance of the bridge was recognized by the crown. The repair techniques themselves were a masterclass in practical engineering. To repair a damaged foundation underwater, they might deploy a cofferdam just as their predecessors had, but on a smaller, more urgent scale. To rebuild a collapsed arch, they would construct a new centering frame, expertly carving new voussoir stones to match the original profile, a testament to the unbroken continuity of their building knowledge. The miracle of these ancient bridges is not that they were built, but that they were so fiercely and intelligently loved, maintained by a web of faith, finance, and civic duty that ensured their silent guardianship over the rivers for centuries. This relentless engineering battle against the river's fury required a deep understanding of hydraulics that seems almost prescient. The wider arch spans we discussed weren't just a stylistic choice from the Gothic era. They were a direct and brilliant response to flood mechanics. A narrower arch acts like a partial dam, constricting the river's flow during high water. This constriction creates a dangerous funnel effect, accelerating the current and increasing its scouring power at the most critical point, the base of the piers. By building fewer, wider arches, medieval engineers effectively gave the floodwaters a much broader avenue to pass through. This reduced the velocity of the water hitting the piers themselves, turning a raging, focused assault into a broader, more manageable flow. The bridge began to work with the river's power instead of fighting it, a fundamental shift in philosophy that greatly enhanced its resilience. The magnificent chapel bridge in Lucerne, with its generous waterway openings, stands as a testament to this principle, having weathered the Reuss River for centuries. The true heroes in this aquatic war, however, are the humble yet supremely intelligent cutwaters. We've mentioned them before, but their design for flood survival is a masterpiece of defensive geometry. These triangular or rounded projections on the upstream side of the piers are far more than decorative add-ons. They are expertly engineered shields. Their primary function is to literally cut the water, diverting the flow smoothly around the pier's vulnerable sides. During a catastrophic flood, this is the difference between survival and collapse. A flat-faced pier would take the full, direct impact of the current, along with any debris it carried uprooted trees, wreckage, even entire structures. The force of that impact would be immense and concentrated. The angled face of a cutwater, by contrast, presents a sloped surface. A log or large piece of debris doesn't smash directly into the stone. It is instead deflected upwards, riding up and over the slope, its destructive energy dissipated harmlessly into the air. Furthermore, the cutwater's shape prevents the formation of powerful, destructive vortices, swirling currents that can dig out the riverbed material from around the pier's foundations, a process known as scouring that is one of the leading causes of bridge failure even today. But the medieval approach to durability went beyond just deflecting force. It also involved a surprising degree of flexibility. While we think of stone bridges as utterly rigid, the best ones were designed with a slight capacity to move, to absorb and redistribute pressure without cracking. This was achieved through the mortar itself. As we've explored, the complex, often organic-laced mortars used were slightly more flexible and less brittle than modern Portland cement. When a flood applied immense pressure to the structure, this mortar could allow for infinitesimal movement between stones, acting as a shock absorber that prevented catastrophic failure. The sheer mass of the structure also played a role. A massive bridge, with its incredibly heavy piers and thick arches, possesses immense inertia. It would resist sudden, shock-loading forces from impacts, favoring instead a slow, constant pressure that its robust design was perfectly suited to handle. This combination of wide spans, intelligent cutwaters, and a degree of flexible forgiveness created a holistic system of flood defense. Each element worked in concert. The wide arches reduced the overall water speed and pressure on the entire structure. The cutwaters managed the localized force and protected against direct impacts, and the construction methods allowed the bridge to give just enough to survive. They understood that you cannot simply build a wall against a river. You must build a partner that can gracefully accept the river's occasional rage and live to tell the tale. This nuanced understanding of natural forces, encoded in stone and mortar, is why so many of these ancient structures still stand today. While countless modern bridges have succumbed to floods, they were theoretically over-engineered to withstand. Moving these titans of stone from the distant quarry to the riverbank was a logistical puzzle of epic proportions, a feat that required not just muscle, but a symphony of coordination, clever physics, and raw, organized manpower. We're talking about blocks weighing several tons each, and a single bridge might require thousands of them. The absence of cranes and trucks wasn't a setback. It was the very constraint that sparked some of the most ingenious solutions in engineering history. The journey began at the quarry, where the newly freed stone was far from ready to travel. The first step was to shape it as much as possible right there at the source. Why transport useless excess weight? Using their templates and tools, masons would rough out the block into a shape much closer to its final form, significantly reducing its mass before it ever moved an inch. But even a rough block was still impossibly heavy. To get it onto a transport vehicle, they employed a fundamental principle: reduce friction. They might dig a ramp down to the base of the block, lay down a path of wooden rollers likely made from sturdy, straight-grained oak, and use levers to painstakingly inch the monolith onto a waiting wooden sledge. The sledge was the heavy hauler of the medieval world, a massively built timber platform, but its secret weapon wasn't its construction, it was its runway. For moving overland, the real challenge wasn't the weight itself, but the drag. The solution was to create a temporary road of smooth, greased timbers laid end to end directly in front of the sledge. A team of oxen, the medieval equivalent of a diesel truck, would pull the sledge forward. As it moved, workers behind it would frantically pick up the now vacated timbers and rush them to the front, laying down the road again. This continuous, rolling pathway drastically reduced the grinding friction that would have made the task impossible. Historical accounts suggest they might have used animal fat or even soap to lubricate these wooden tracks, creating a slick surface that allowed a dozen oxen to pull a load that would otherwise have required 100. When the terrain allowed, especially for the final approach to the river, they might forego the timber track and use rollers alone. This was a more precarious method, requiring immense skill from the team guiding the rollers to keep the load stable and moving in a straight line. The coordination was breathtaking, the shouts of the ox drivers, the creak of the massive timbers, the teams of men constantly resetting the path, all to move a single block a few agonizingly slow feet at a time. The pace was glacial, perhaps only a mile or two in an entire day's grueling labor, but the real game changer for bridge construction was the river itself. Once the block reached the bank, the overland ordeal was over. Here, the builders could harness the natural highway that the bridge itself would eventually span. The stone blocks were carefully loaded onto wide, flat-bottomed barges, designed for stability rather than speed. These vessels were the silent workhorses of the operation. Tethered together and guided by teams in smaller boats, they formed a slow-moving procession of stone, floating the immense weight with an efficiency that land transport could never match. The current itself could be used to assist the journey downstream, while moving stones upstream would require teams of men or animals walking along the towpaths on the riverbank, dragging the barges against the flow with long ropes. This entire operation, from quarry to barge, was a masterpiece of medieval project management. It required a quartermaster's mind to coordinate the endless supply of timber for tracks and rollers, the care and feeding of large ox teams, the building and maintenance of barges, and the housing and feeding of the hundreds of workers involved. A master mason wasn't just an architect, he was a CEO and a logistics commander, orchestrating this chaotic, slow-motion ballet of men, animals, and stone. The successful movement of a single keystone block was a victory earned through sheer tenacity and organizational brilliance, a hidden triumph that made the visible miracle of the arch above possible. And for all their ingenuity, medieval bridge builders were not infallible. For every stunning success like the Pont d'Avignon, there were heartbreaking, catastrophic failures, bridges that collapsed during construction or crumbled into the river just years after their triumphant opening. These disasters were not just tragic losses of life and treasure, they were brutal, unforgiving lessons in physics, geology, and material science. Each collapse forced a painful but essential reevaluation of techniques, becoming the crucible in which medieval engineering was truly tested and refined. One of the most common and devastating points of failure was the foundation. We've marveled at the cofferdam, but its success was never guaranteed. A sudden rise in the river could overwhelm the clay seals, flooding the workspace and washing away the unset mortar of a partially built pier, setting the project back months. More insidiously, a builder could misjudge the riverbed itself. If they did not excavate deeply enough to reach a firm, stable stratum, what we would now call bedrock or a competent bearing layer, the entire massive weight of the pier would be resting on compacted sand or gravel. Over time, or under the immense pressure of a flood, this softer material could compress or shift, causing the pier to settle unevenly. This differential settlement is a death sentence for a masonry arch, as it introduces stresses the rigid stone structure cannot accommodate, leading to cracks and ultimately, a sudden, catastrophic collapse. The London Bridge of 1825, which replaced the medieval original, famously experienced this. but its medieval predecessors were just as vulnerable. The original bridge itself had multiple collapses throughout its history, with fires and ice flows contributing to its woes. These events taught builders the paramount importance of truly understanding what lay beneath the water. They became more meticulous in their probing of the riverbed, likely using long iron rods to test the depth of soft sediment before committing to a cofferdam location. They also learned to build wider foundation platforms, distributing the immense load of the pier over a greater area of the unstable riverbed to prevent it from sinking, a pragmatic solution born from bitter experience. Another critical lesson came from understanding the river as a dynamic, living system, not just a body of water to be spanned. A famous and oft-cited example is the collapse of the original bridge at Regensburg before the current Steinerne was built. The story, likely passed down through generations of masons, tells of the chief engineer making a pact with the devil to ensure the bridge's completion, a folklore trope that often masks a real historical catastrophe. The likely truth is that the initial design failed to account for the tremendous scouring power of the Danube River during its spring floods. The current, funneled between too many piers, may have excavated the riverbed around the foundations, undermining their stability until the entire structure gave way. This hard-won knowledge is visibly etched into the bridges that survived. The subsequent design of the Steinerne, with its robust piers and generous arches, shows a profound respect for the river's power. Similarly, the repeated collapses of earlier bridges at places like Avignon directly informed the stronger, more resilient designs that followed. Each disaster was a gruesome full-scale experiment that provided irrefutable data on flow rates, ice pressure, and foundation integrity. This knowledge was then encoded into the guild's oral traditions and practical rules of thumb rules about pier spacing, arch steepness, and foundation depth that were passed from master to apprentice, ensuring that the same mistakes would not be made twice. The silent, enduring bridges we admire today are not just monuments to success. They are also memorials to their fallen predecessors, embodying the hard lessons learned from failure and standing as a testament to the resilience of the human spirit in the face of monumental challenge. This incredible diversity in design wasn't simply a matter of different architects having different tastes. It was a direct and eloquent response to the unique personality of each place. A bridge in the rainy, war-torn north of France had a completely different set of problems to solve than one in the sun-drenched, merchant-rich city-states of Italy. The materials at hand, the political climate, the primary purpose of the crossing, all of these factors conspired to create distinct regional styles that tell us as much about medieval life as any history book. Consider the stark, military might of the fortified bridges found throughout France, like the previously mentioned Pont or the fortified bridge at Orthez. These regions were often battlegrounds, either during the 100 Years' War or in the constant feudal squabbles between local lords. The river wasn't just a geographic feature, it was a defensive moat on a grand scale. The primary threat here was human invasion, so the bridge's design prioritized defense above all else. The result was a structure that was less a crossing and more a linear castle. Towering gatehouses with heavy iron portcullises, crenellated parapets for archers, and integrated garrison chambers weren't added decorations. They were the entire point. The bridge itself became a fortified border checkpoint, capable of controlling and taxing all movement while presenting a formidable obstacle to any army. The local limestone, easy to cut into massive blocks, was perfect for building these thick, impenetrable walls, making the bridge a permanent statement of military power and territorial control. Now, travel south to the vibrant, competing republics of Italy, and you find a completely different philosophy embodied in a bridge like the Pont Vecchio in Florence. Here, the greatest threat wasn't an invading army, but a rival city-state gaining an economic advantage. The priority was wealth generation and civic prestige. These were centers of international finance and trade, and the bridge became an extension of the bustling marketplace. Building directly over the valuable riverfront real estate was a brilliant urban planning solution, creating prime retail space that also generated a continuous income stream for the city's coffers. The famous jewelry shops lining the Pont Vecchio are a direct continuation of this medieval mercantile tradition. The design is open, almost celebratory, with large arches to facilitate river traffic carrying goods, and wide decks to accommodate crowds of shoppers. The building materials often included more elegant, finely carved stone and decorative elements to showcase the city's wealth and refinement. The bridge was a commercial engine and a symbol of civic pride, not a defensive bulwark. Venture into the rugged, mountainous terrain of Switzerland and parts of southern Germany, and you encounter a third distinct style shaped by a formidable natural adversary: alpine floods. Bridges like the Capelbrook in Lucerne or those spanning the Rhine tributaries had to be designed to withstand not just water, but the devastating force of spring snowmelt carrying massive debris. The solution was often the covered wooden bridge. The roof wasn't primarily for sheltering people. It was a crucial structural and preservation element. It protected the massive timber trusses from constant soaking and drying, which would cause the wood to rot and warp far more quickly. The intricate triangular truss designs, like those of the Capelbrook, were engineered to distribute these immense hydraulic loads across the entire structure, allowing it to absorb and dissipate energy. The availability of vast forests meant wood was the primary building material, and these communities developed an unparalleled expertise in complex timber framing to turn this abundant resource into a weapon against the violent, unpredictable mountain rivers. Even the humble, everyday bridges of the English countryside tell a story of local priorities and materials. In regions rich in good building stone, like the Cotswolds, you find sturdy, no-nonsense packhorse bridges with low, graceful arches. Their NRROW Chinese letter was designed for trains of packhorses, not carts, reflecting the local trade routes. In areas where good stone was scarce, like parts of East Anglia, brick became the default material, leading to a distinctly different aesthetic. The presence or absence of a chapel on the bridge also speaks volumes. In remote areas, a bridge chapel offered a lonely traveler a moment of prayer for safe passage ahead, a spiritual refuge. On a busy urban bridge, the chapel was often larger, serving as a venue for meetings, a place to collect tolls, and a landmark. From the quarried stone to the very purpose of its attachments, every medieval bridge was a deep dialogue with its environment, a frozen moment of practical and cultural logic that turned mere infrastructure into a portrait of a place and its people. This culture of secrecy wasn't just about protecting job security. It was a matter of life and death for the structure itself. A poorly trained mason, even with the best intentions, could introduce a fatal flaw, a miscalculated arch, an improperly mixed mortar, that might only reveal itself decades later in a catastrophic collapse. The guild's entire reputation, built over generations, rested on the flawless execution of every project. This immense responsibility justified their rigid control. An apprentice's training was a multi-stage journey designed to weed out the uncommitted and imperceptive. It began with years of performing the most menial tasks, mixing mortar, hauling materials, and simply observing. This period, which could last 7 years or more, was as much a test of character as it was of skill. Was the young man patient? Was he attentive? Could he be trusted with the lodge's most precious asset, its knowledge? The heart of this secret knowledge was the Lodge Secrets, a collection of practical techniques, geometric rules, and proprietary material recipes that were never written down. These were communicated orally, often in coded language or through intricate hand gestures, during carefully staged initiation ceremonies. A journeyman advancing to the rank of master would undergo a ritual that reenacted the spiritual journey of the mythical architect Hiram Abiff, the central figure in Masonic lore. This ritual, full of symbolism about death and rebirth, was a profound psychological experience designed to impress upon the candidate the sacred weight of the responsibility he was about to assume. He would swear a blood oath never to reveal the secrets of the craft to outsiders, under penalty of exile or worse. Only after this oath was he entrusted with the final, most powerful knowledge, The precise geometric formula for setting out a stable arch, the alchemical recipe for the waterproof mortar, or the method for calculating the precise angle of a cutwater. This system of oral transmission created a living, evolving repository of knowledge, but it also made the information incredibly fragile. If a master mason died unexpectedly without passing on a key piece of information, that technique could be lost to his lodge forever. This is likely why we see such strong regional styles in medieval bridges. Each guild developed its own slightly different solutions to common problems, and these became their signature, their competitive edge. The secret symbols we find carved into bridge stones, the mason's marks, were part of this system. While they served the practical purpose of identifying a craftsman's work for payment, they also functioned as a silent language among the initiated. A particular symbol might not only identify the man, but also his home lodge and perhaps even his level of mastery, allowing a traveling mason to prove his credentials and find work on a distant site without saying a word. This invisible network of symbols and rituals bound the fraternity together across Europe, creating an international brotherhood of builders who spoke the silent, universal language of stone. Yet beyond the practical considerations of defense and commerce, there lies a far more enigmatic layer to the placement of these structures, one that hints at a world where engineering and esoteric knowledge were deeply intertwined. While most bridges were unquestionably sited for the most pragmatic of reasons, the narrowest crossing point, the most stable riverbed, a handful of exceptional examples present a compelling mystery. There is a controversial but fascinating body of evidence suggesting that some medieval bridges were precisely aligned with significant celestial events or sacred geographical directions, embedding a layer of cosmic and spiritual symbolism right into the landscape. Consider the possibility that the master mason, a man steeped in the geometric and harmonic principles believed to govern God's creation, might also have been versed in the movements of the heavens. For a deeply religious society, the sky was not a random collection of lights. It was a divine clockwork, a mirror of heavenly order. Aligning a bridge, a crucial lifeline between communities of souls, to a celestial event could have been seen as a way to consecrate the structure, to bless it with the harmony of the cosmos itself. One of the most debated examples is the alignment of the ancient bridge at St. Bénézet, the Pont d'Avignon. Some researchers have pointed out that the original orientation of its surviving arches creates a precise alignment with the rising sun on the feast day of St. John the Baptist, a figure of immense importance in medieval spirituality associated with purification and crossing thresholds. On that specific morning, the sun would have risen directly in line with the bridge's axis, potentially flooding the structure with light in a dramatic, symbolic event. This idea extends beyond solar alignments to the very stars themselves. In an age before GPS or even accurate maps, long-distance travel relied on natural landmarks and the fixed points of the night sky. A bridge, as the key node in a network of pilgrimage routes or trade roads, might have been deliberately placed to serve as a terrestrial marker corresponding to a celestial one. A pilgrim traveling at night could have used the North Star, positioned directly over a specific bridge's profile, to confirm they were on the correct path. This transforms the bridge from a passive crossing into an active navigational aid, a stone compass needle fixed in the earth. The orientation of certain bridges in relation to prominent local churches or shrines further complicates the picture. Some appear to form perfect ley lines, straight, energetic pathways across the landscape, connecting ancient sites of power, though this theory is often dismissed by mainstream academics as modern fancy. However, the alignment of a bridge's central axis directly with the high altar of a distant cathedral, ensuring a perfect symbolic and visual connection between the spiritual heart of a community and its physical gateway, is a documented phenomenon that speaks to a profound intentionality in its placement. Skeptics, of course, argue convincingly that any such alignments are mere coincidence, the product of overactive imagination applied to the limited number of viable crossing points on a river. They maintain that the primary drivers were always economics, geology, and defense. Yet, For the master masons and their clerical patrons who blended Pythagorean geometry with Christian theology, the universe was a web of interconnected symbols and meanings. To build a bridge that not only served humanity, but also echoed the harmony of the spheres would have been the ultimate act of devotion, a way to build a piece of heaven here on earth. Whether by deliberate design or happy accident, these potential alignments invite us to look at these structures not just as feats of engineering, but as potential stone prayers, oriented not just toward the other bank, but toward the infinite. For centuries, the true genius of these medieval builders was locked within the stone, invisible to the naked eye and known only through the legends they left behind. But today, we're no longer limited to historical documents or surface observation. Modern science has given us a new set of eyes, incredibly precise tools that allow us to peer right through the masonry and decode the secrets these master masons never wrote down. The findings are not just confirming their skill, they're completely revolutionizing our understanding of it. Take ground-penetrating radar, for instance. This technology sends electromagnetic pulses into the ground and builds a picture from the reflected signals, acting like an X-ray for the Earth. When researchers used it on the foundations of bridges like the Pont they made a staggering discovery. The foundations weren't just simple, stacked platforms as many had assumed. The radar revealed complex, multi-layered subterranean structures, deep pilings made of tightly packed timber driven far into the riverbed, acting like the roots of a giant tree to stabilize the pier above. In some cases, they found that the builders had intentionally filled in entire sections of the riverbed with tons of rubble and stone to create an artificial, reinforced island upon which to build, a technique that was completely invisible and unknown until now. This wasn't guesswork, it was a profound, calculated understanding of soil mechanics. Then there's 3D laser scanning, which creates a hyper-accurate digital twin of a structure. By mapping every single stone on a bridge like the Charles Bridge to a sub-millimeter precision, engineers can detect patterns of wear and stress that are imperceptible to someone standing on it. This analysis has shown how medieval arches actually move and settle under load in a delicate, balanced dance. The scans can reveal how the thrust lines, the paths along which the weight of the bridge travels, are perfectly channeled through the stonework, often aligning exactly with the geometric principles the masons would have used. This digital modeling allows us to see the bridge not as a static monument, but as a dynamic, living system, and it proves that its stability is no accident. It's the direct result of immaculate geometric calculation. Perhaps the most revelatory work is happening in the laboratory, with advanced material analysis of the mortar. Using techniques like X-ray diffraction and scanning electron microscopy, scientists can break down the chemical composition of 800-year-old mortar to its atomic level. And what they're finding is astonishing. These were not simple lime mortars. The analysis consistently shows the presence of crystalline compounds like calcium silicate hydrate, the very same compound that gives modern concrete its strength and hydraulic properties. This confirms the use of pozzolanic additives like crushed brick or volcanic ash, creating a chemical reaction that made the mortar stronger over centuries, not weaker. The microscope has even detected microscopic, hollow spheres within the mortar matrix, potential evidence of those legendary organic additives like animal blood or egg whites, which would have created these tiny bubbles to absorb the stress of freezing and thawing. Science is now validating the ancient recipes that were once dismissed as mere folklore. This fusion of historical study and cutting-edge technology is giving us the clearest picture yet of the medieval master mason's mind. He was part architect, part materials scientist, and part geotechnical engineer. He understood that a bridge was a conversation between the stone above the water and the earth below it, and he engineered solutions for both with a sophistication we are only just beginning to fully appreciate. The scanners and microscopes aren't diminishing their achievements. They are finally giving us the language to understand the full breadth of their brilliance, revealing that the real magic wasn't in any supernatural pact, but in an utterly masterful command of the physical world. So what can we, with all our computational power and advanced materials, possibly learn from these ancient craftsmen? The answer is not in copying their designs, but in understanding their philosophy. They worked with nature, not against it. Their pointed arches and starling cutwaters didn't fight the river's force. They redirected it, managed it, and dissipated its energy. They built for resilience and adaptability, creating structures that could tolerate slight movements and settle over time without catastrophic failure. They used local materials, designed for easy maintenance, and created self-funding models for perpetual upkeep. In an age obsessed with speed and cost efficiency, their patient, holistic approach to engineering, where a project was a 100-year endeavor, not a 2-year contract, offers a profound lesson in sustainability and long-term thinking. The true secret wasn't a hidden formula. It was a mindset of deep observation, respect for materials, and an unwavering commitment to building for the ages. This legacy is not locked away in archives. It's standing in plain sight, waiting for us to cross it. I encourage you to seek out these ancient wonders for yourself. Walk across the worn stones of the Pont Vecchio in Florence and feel the hum of centuries of commerce beneath your feet. Stand before the formidable towers of the Pont Vale and sense the military ambition it was designed to project. Trace the masons' marks on the Charles Bridge and try to decipher the silent signatures of the hands that shaped them. When you do, you're not just looking at an old bridge. You are walking across the culmination of forgotten science, sacred geometry, and raw human determination. You are experiencing a mystery carved in stone, a testament to the fact that true ingenuity is, and always will be,